Hello everyone. I'm very excited to be here and thank you for being in my talk. My name is Amit Finkman, and in the next 40 minutes, I'm going to present you CodeCloak, a DRL-based method in order to mitigate code leakage while using AI code assistant models. So this talk is based on a paper with the same name. So if anyone would like to read about it further later, he can scan the QR code that's attached here. So, before we dive in about what is actually CodeCloak, first I would like to introduce me and my team, because of course CodeCloak is not one-man effort. So as I mentioned, my name is Amit Finkman, I'm 27 years old, and I'm currently pursuing my master's degree in Information System and Engineering from Ben-Gurion University, with specialty in machine learning and AI. My bachelor degree is also from Ben-Gurion University in Data Science and Engineering. At the past 2 years, I'm working as AI and cybersecurity researcher at the CBG Labs with collaboration with Deutsche Telekom. Working with me on this project, Eden Bar-Kochva, Avishak Shapira, Dudu Mimran, Inbar Maimon, Professor Asaf Shabtai, and Professor Yuval Alovich. So I would like that we will go over the agenda quickly. First, I will start with some brief background about what is AI code assistant models and the powerfulness of using them. Then I will show the risks of using those AI code assistants. Then I will show our solution, which is CodeCloak, that comes to solve the risks. Then I will show some key takeaways that I would like that you will take from this talk. Then I will show some future steps, and lastly, questions and answers. So let's start with the background. So the revolution of the AI changed our world in many ways, and software development is one of them. Today, any developer will know or even is using at least one of the above, if it's GitHub Copilot, Code Whisper, Tabneen, GitHub Copilot, Codium, StarCoder, Code Llama, and on. These tools help the developers to rewrite, fix, and improve code quickly. In addition, they make coding much faster and much easier by providing real-time suggestions and even creating entire parts of source code. They save time, they reduce mistakes, and let the developers to focus on more creative work. So for the both of you who doesn't know how it actually works, I would like to present a quick example now. So let's say, we look at the screen. So let's say that this is what the developer already typed. Let's say that this is the cursor position. It means where the developer is currently coding. And here in gray, you can find the suggestions that was offered by the AI code assistant of how to complete us. So what is really happening? So let's say that now I'm the developer who currently coding. The source code that will be written on the IDE, as we saw in the example before. Behind the scenes, the source code will be sent via prompts, and from now on, when I'm saying prompts, the meaning is the source code that was sent to the AI code assistant. Then, the AI code assistant will now, based on the source code that it will get, generate a meaningful suggestion that will be written back on the IDE, as we saw in the example. So from now on, when I'm saying suggestions, the meaning is to the completion of how the AI code assistant offers to complete us. So you may think that when you use those AI assistants, only a couple lines of code is being sent in order to generate meaningful suggestions. But in reality, we found out that this is not the case. In our research, we found out that very often that in order to generate meaningful suggestions, it means that an aggressive amount of source code needs to be sent in order to generate meaningful suggestions. It could contain from your full file, many files, or even entire parts of your repositories. So this leads us to the threat model. So why does it a risk? What is the problem with it? The reason stems from the fact that in order to provide those suggestions, the prompt that I just mentioned, which the source code is being sent, are sent to the service provider where the AI model runs. It means that it can expose sensitive data or property code to the service provider or even to attackers if someone manages to steal the data while it's being sent. For developers working on sensitive projects, for example, there is a big risk for their project are being leaked, and there is a danger that they jeopardize their organization's private code. In a worst-case scenario, an entire code base could be reconstructed by analyzing those snippets, which can lead to serious privacy and security concerns. So now I will show some articles about big companies that bend to their employments use those assistants, such as Samsung, Big Tech, Google, Apple. We found out there's a potential intellectual property violation. Moreover, we wanted to demonstrate how an attacker could reconstruct those code segments, and in order to do this, to quantify and assess how much of the code base might be leaked, we created a system to analyze the potential leakage. So first, we placed the proxy to capture the user prompts that's sent from the IDE to the AI code assistant. This is done in the data leakage monitor. Then, the source code will be moved to the data pre-processing step, where the captured prompts are reorganized into smaller segments, and then the source code will be sent to the code reconstruction component, where we use an LLM to rebuild the original code from those segments. Lastly, after this reconstruction component will reconstruct, this is the original file from those prompts, we will send it to the evaluation component in order to compare between the original source code and the reconstructed source code. This is done in order to determine how much of the code base might be exposed. So here we can see how the LLM helps to reconstruct the developer's code, which is demonstrating how much of the original code might be recovered from those prompts sent during coding. So here we can see the system prompt, what is the LLM instruct to do. Here we can see the user prompts, and using the LLM, we can reconstruct the code base. So I would like to remind what we saw until now. I saw the powerfulness of using AI, and now I'm showing the risks of using them. So in our research from this prompt, we found out that the service provider, we succeed to recover on average 80% of the source codes. So now we understand that there is a very big risk, and this leads us to the solution, which is our CodeCloak. So when we started to work on this project, we thought, what are the goals that we want to achieve? And it will lead us that we want first to protecting the intellectual property, because we want to mitigate the risk of property or sensitive code might be leaked exposed. Second, we would like to protect an organizations because we want to reduce the risk of security breaches and reputational damage. And last, we would like to empower the AI code assistant models because we want to mitigate the risk of property or sensitive code being exposed to third-party servers or even access to attackers. So in our research, we would like to achieve two main goals. First, we would like to reduce the leakage as much as we can by changing the prompt in a way that such less code will be leaked. And we want to do this while we want to preserve the AI code assistant productivity. Moreover, in our research, the main hypothesis that not all of the source code is actually being sent is actually really needed in order to provide a good suggestions. So you know what? Let's see how CodeCloak, our solution, works in practice. So on the left image, we can see the original prompt that was sent to the AI code assistant, where we can see a lot of sensitive data, such as function names, their body. We can see that there is a lot of lines of code. And on the right image, we can see the same prompt after it was manipulated and was modified using our CodeCloak. Here, we can see that the function's names were modified and using a hash, and the function's body was altered using a summarization local model. However, despite those changes, we can still see that the AI code assistant provided the same suggestions. So now that we understand that CodeCloak is well effective, I would like to explain the backbones behind it. And in order to do this, in the next few minutes, I will explain to you what is reinforcement learning, or RL. So reinforcement learning is a type of machine learning that is inspired by humans of how they learn to make complete tasks by trial and error. So imagine that we want to teaching the robot to navigate within the grid. The robot goal will be to get the green flag while avoiding the fire. So the robot will try different ways. If it will move closer to the flag, it will get a benefit. But if it will move closer to the fire, it will get a penalty. So over the time, the robot will learn which ways it should avoid and which ways it should to focus on. In this way, it will discover the best way to navigate within the grid. An episode in RL refers to one complete attempt that the robot makes to navigate from the start to the end, and each episode allows the robot to explore, learn from its mistakes, and improve its strategy for future episodes. So moreover, you can think that in our method, CodeCloak works just like this robot. It learns to manipulate the source code in order to reduce the leakage while maintaining the suggestions useful and relevant. Moreover, the reason that we chose reinforcement learning in our task is because RL is well suited for decision-making problems. In our case, the task involves which manipulation to apply to the code prompt at each time step to reduce the leakage while maintaining the usefulness. And RL is well fit for this scenario because it learns by trial and error, optimizing decisions over the time to achieve the best balance between the objectives. So now that we understand the main components of the main subject idea behind RL, I would like to explain the three main components that it relies on, which are states, actions, and rewards. You can think about the state like where we are now, actions, what we can do, and the rewards is the feedback for doing it right. So let's start with the states. In our robot example, the state is the current position of the robot within the grid environment. We can see that the start position is located on 1, 2. Understanding those coordinations will help the robot to decide his next move within the grid environment. Second, the actions. So the actions reflect the all possible moves that our robot can do in the grid environment. In our case, it will be up, down, left, or right. At every step, it will choose the best action based on what it learned. And lastly, the rewards. If the robot will move closer to the fire, it will get a penalty. But if it will move closer to the flag, it will get a benefit. Over the time, from learning from those rewards and penalties, the robot will figure out the best way to navigate within the grid environment in order to reach its goal safely. So, here we can see that the robot is located on 3, 3, and it chose to go right. Because he reached his goal, it will get a positive reward of 100 scores. So now that we understand the basic concept and the components of the RL, it is important to say that in the real world, the traditional RL is only effective for simple toy environments. This is because RL relies on straightforward representation of the environment, and it struggles when dealing with complex, high-dimensional data. And this is where deep reinforcement learning comes into play, because the DRL addresses those challenges by combining RL with deep learning. The neural networks in the DRL can process raw, unstructured data and extract meaningful patterns. DRL also scales well in large environments with many possible states and actions, which is making it well suitable for real-time applications such as robotics, autonomous systems, or in our case, manipulate source codes for our CodeCloak. So now we can finally explain how we modeled our problem. And it's important to say that although the DRL using the neural networks, it also relies on the same three main components as the traditional RL. So let's start with the states. So first, in order to deal with the large amount of source code, we chose to first split up the original prompt into segments. Now, each segment will be manipulated independently to reduce the leakage. This approach will fine-grained control over changes while minimizing the disruption of the overall prompt. The key idea behind it is to iteratively manipulate segments in order to reduce the leakage. This approach will enable iterative and focused adjustment for each part of the prompt. So it's important to mention that in every step, our agent will get another segment. So in our example, the full source code will be after the free segment. So in each state, we will focus on three different things. First, we would like to focus on the prompt embedding, because in the first case, we chose to use the raw text as the input of our state. But then we realized that it could be very sparse, and in order to deal with it, we used a pre-trained encoder model that was adjusted especially for source code. Second, we will use the relative location, which will mean which segment we're currently working on. And lastly, we will use the cursor position because it extremely and very makes sense influence on the suggestion that the AI code assistant generates. So second, the actions refers to the all modification that we can apply on each segment within the prompt. This is defined as operation on the segment. So now let's see some examples about any manipulations that our robot can, that our agent can do, such as detect and replace personal information, change, delete, or insert random lines, delete functions body and replace it with summaries, or rename variables functions, stop manipulations, and send it to the AI code assistant. So it's important to mention that at every step, another segment will be manipulated. And that lastly, we will get a series of modifications that we can apply on the source code. So let's see an example. Let's say that this is our original prompt, and for simplicity, let's say that we have only one segment. Let's say that our agent chose to delete lines, and this is how our prompt will look like after the manipulation. And lastly, in order to explain how we calculated the reward in our solution, I would like to explain shortly what is the CodeBlue metric. So the CodeBlue metric is a well-known metric that expands the traditional blue score. It captures different aspects of similarity between source code, such as functionality similarity or visual similarity, which is based on n-grams, AST, and data flow matches. So when we calculated the reward in our problem, we would like to focus on three main things. First, we would like to balance the trade-off because our solution minimized the code leakage by reducing similarity between the original and manipulated prompts while ensuring high quality of the suggestions. Second, we would like to interact with our agent in real time because we want to analyze the suggestions in the real time. And lastly, we would like to calculate the reward using our CodeBlue metric. We would like to minimize the similarity between the prompts and maximize the similarity between the suggestions. So let's see an example how it calculated in practice. So let's take the prompt that was manipulated from our last example, and let's take the original prompt. So based on the CodeBlue score, we can see the similarity is 0.83. Now, this is the suggestions that was offered by the AI code assistant. Here, because we see that the suggestions are exactly the same, the CodeBlue score will be 1. And now, because we want to maximize the difference between the prompts and minimize the difference between the suggestions, we can see that the reward is calculated by the CodeBlue score of the suggestions minus the CodeBlue scores of the prompts. So now we can finally talk about how we train the DRL agent. So now, we first created prompts dataset. So now let's assume that this dataset is just existing, and in one slide later, I will explain how we implemented it. So now we will take the full prompt. This prompt will be sent, we split up into segments. Then we will send the first segment to our DRL agent. The DRL agent will now choose which manipulation to apply. Let's say that in this case, it chose to delete lines. We will send the full prompt to our code assistant service. Now the code assistant service will generate a suggestion. The suggestion will be sent back to the DRL agent. Now the DRL agent will calculate the reward based on what we said before. Now we will send the second segment to our DRL agent. Now the DRL agent will choose to change names. We will send again the full prompt to the code assistant service. Now the code assistant service will generate another suggestion that will be sent back to the DRL agent. Again, the DRL agent will calculate the reward. And lastly, after many steps and episodes, that in every episode the DRL agent will get another prompt, we will get our trained agent. So, how we actually implemented the dataset. So when we first started to work on this project, we realized that there is not any existing dataset that simulates developers typing interacting with AI code assistants in real time. This kind of dataset is well crucial for our task because we understand that it captures the dynamic nature and the decisions that developers make as they write code. In order to address this gap, we created our own dataset that's specially designed for source code that reflects the real-time coding scenarios. Thus, we created the developer coding simulation. This will run within an IDE configured with the AI Code Assistant plugin. Second, it will try to simulate a real-world development process by it will introduce coding errors at random intervals. It will correct the errors after writing additional lines of code. It will simulate pauses in typing and back and forth on the navigation, and it will maintain average typing speed of a developer. So now let's see how it works. We can see that the simulator goes up and down. It made some deletions. And finally, we will get the completion of how the AI Code Assistant offered to complete us. So finally, after we show the powerfulness of using the AI Code Assistant, we show the problems and the risks of using those AI Code Assistant. We talked about our solution, how we implemented it, and how we used it. I would like to show a quick demo that we created in order to present how our method works at inference time. So let's take a look. So here we can see how the developer is currently working on without our DRL agent. We can see that there is a large amount of source code that is being leaked. Now we can see how our AI agent will work after we're using the CodeCloak. We can see that we succeed to reduce the amount of the code that's being leaked in a significant way. And the developer will not notice what is the process that happens behind him. So great. So I would like to explain how we did the evaluation setup. So first, the dataset that we used were unseen prompts from our custom dataset. Second, the code assistant that will be used were two well-known AI open source code assistants, which is StarCoder and Code Llama. And now I would like to show the key results from our research. So first, we found out that CodeCloak is well effective for privacy protection. We found out that our solution reduced the code leakage by an average 40%, which is significantly minimizing the risk of exposing sensitive code segments. Second, we achieved high quality on the suggestions based on the CodeBlue metric, and we found out that on average 75% of the code will remain useful and for the real-world tasks. Third, this CodeCloak consists from minimal overhead for large code bases. We saw that it added only slight processing time, which making our solution well practical. And lastly, we saw that CodeCloak is well effective for different prompts and different AI code assistant, making it adaptable for real-time and environments and setups. So here we can see that the action distribution heat map in the test time of our method. At the x-axis, we can see the manipulations, which means which manipulation we can apply on our source code. At the y-axis, we can see the time step, which means how many modifications we did to our source code until now. So moreover, in our real application and real implementation, we chose to restrict the number of steps to be at most 15 because we wanted that CodeCloak will work in real-time applications. So we can see from the image that during the initial step of the process, our solution tends to apply more aggressive manipulations, such as functions body, deletes functions body. We can see it in the first line, the yellow boxes. And this indicating that the agent prioritizing to reduce the leakage by focusing on significant modifications early on. Moreover, as the process continues, the agent transitions to more refined actions, such as change variable names, which are fine-tune the suggestions while preserving the relevance. So now I will show you the main key takeaways that I would like that you will take from this talk. So first, we found out that code leakage is a real threat, but now it's well fixable using our solution. Second, we found out that using our solution, which is CodeCloak, we can balance between the privacy and the productivity of the AI code assistant. And lastly, the CodeCloak sets a new benchmark for mitigating AI-related security risks. So now some future steps we are planning to do in the future. So first, we would like to enhance the adaptability of our solution because we want to explore how CodeCloak can be generalized across a wide range of programming languages and frameworks. Second, we would like to reduce the overhead because we want to optimize CodeCloak to performance and minimize the computational overhead during real-time use. We would like to integrate it with the IDEs because we want to develop seamless integrations to popular IDEs to make CodeCloak more accessible for developers. And lastly, we would like to open source it because we want that CodeCloak will encourage community-driven improvement. So this is some references that I used in order to create this presentation. And that's all. We have some time for questions. If someone would like to ask me questions, I'm here. That's all. Thank you very much.
When you're changing variables and function names, do you have some translation back? Previous names, what translation will actually...
Okay, so the question is when we're changing the variables and the argument names, if there is any reverse for this, is a reverse back to this transition. So the answer is yes. We used a component of the code translation. We are keeping an hash of our manipulations, and then when we revert back the suggestion, we also were changing back to the original names. Okay. Any other question? So if not, thank you for your time and for attending to this talk. That's all. Thank you very much.